Get one of these. Oh, they're so small.
All right. Well, I mean, these are all the people that go to class.
Essentially.
Op amps are pretty much universally where everyone did bad. A big thing is just, getting the right equation for VP and VN. So just thinking about all of your op amp circuits, any configuration that we can give you, you should be able to find some expression for VP and VN from KVL and KCL. Having positive and negative feedback. Something that'll happen a lot. But take like a simple one that we had on the homework. Trying to find the expression for V out. Being able to get your VP and VN equations. And that's
Okay. 3 foot width.
90% of the problems. That was the hard thing on
Okay, mark the bottom,
exam too, is that we set that up right or wrong. Very hard to get any points. Part 2 directly needed you to have part 1A, part 1 right. So I don't know if there's any confusion on what this is, right? Because it's an ideal op amp, the gain is infinite, which means that there has to be very small difference in VP and VN to be multiplied to a certain value. So gain goes to infinity. VP is gonna be approximately like the same as V10. But we use this not as the values, but to find the expressions for them. You could use them for the values, but primarily when we're looking at it and we're solving it symbolically, we're looking to find an expression and set those expressions equal to each other. So I don't know if you guys want to run through the example or if it's just like talking about it. So VP is really easy to find. We know that no current's going to go through here into the op amp. So this just becomes a voltage divider. VN is where you did that practice of using V out. You want VP and VN in terms of input and output voltages or sources. So VN in terms of that is going to be this voltage drop plus that to ground. Could go the other way. I've done this way before, so I'm gonna go this way. But I mean that we're gonna have to be careful with signs, right? that. So. Anyone want to take a crack at it?
V out minus V out, we're on just VR.
Hey, that gives us what?
That gives you a-
That gives us current, right?
Mhm.
That gives us the current flowing through R2 and R1 because no current's flowing into the op amp.
Yes.
What direction is that current flowing? This is where some issues can come up if you don't keep track of your signs. Towards V out? You did V out minus V in. So current's going this way. So now we have. That's the current. Multiplied by R1. And. G. All that is equal to what? Hmm? So we have current times the resistance, we have a voltage here. Plus EG. And if you're taking this equation, right, if you're saying the current through this resistor times this resistor. Yeah. So you're saying that this drop plus this drop, that's equal to Vn. Now. This way is harder than going the other way. Because now we have to do algebra. And get it to be Vn equals some expression.
Should we put plus V out?
Should you do plus V out?
Yeah, because you're going the other way to ground.
Oh, yeah. Oh,
Yeah, so normally. I go this way.
yeah.
Because it's easier to work with. I did this other way to show. the example. And also to. Kind of point you guys to be very careful with your signs and your algebra. That part's gonna be. I don't know, it's tricky for me. Um. You have your inspires, so you could do like symbolic solve, which is great. It'll save you a lot of time and help you double check your work. I will preferably leave that up to you guys to work out, but what's the expression that we should get for Vn? Or, yes, for Vn. Going to be.
So. But I did affect for.
Believe so.
If you wanna go this way,
Yeah, that's what I did.
that's better.
I do need help checking my work. Well,
Or if you were going the other way, wouldn't you do V out minus EG still? To get the current?
couldn't I do what?
Or wouldn't that still work even if you went the other direction?
You have to be careful with your sign. You did B out minus EG?
Oh, yeah, well,
Cause you're,
if you're gonna be like,
if I'm saying V out minus, or the way that I said it there is so that I can have current going this way.
no, I meant for the first one.
For the first equation?
Yeah.
Could you do? Yeah. And then do,
Yeah,
right, and that'll give you current going this way. And you could still do it. That's it, easy.
Still times R1 dash.
yeah.
Yeah, it's only doing just change the equation for the prime.
And that makes it a lot easier to get to the.
Yes.
All right, that works.
Yeah, it's just on the next part when you set them equal to each other, it's gonna be. Yeah, but you take your VN equation. And your VP equations, and you set them equal to each other. From there, you can solve for V out. This one.
I guess we're gonna get our plan with good blessing.
That's what I'm wondering.
Like, it's the way Russell's exams work. I haven't seen it. But, yeah, it was like first one. So you're definitely gonna see it again.
With a capacity, that's what,
Oh, with a capacitor?
like we covered. it in the
Differential ones, yeah.
Uh. I doubt it. But I also don't want to be the TA that says I doubt it, and then you guys get it. Seems more of a question that you get in circuits too anyway.
You might be the sense like,
Yeah,
this is something that you'll have to deal with in the future.
well, no, he was like, this might be on the test,
Uh-huh.
like twice.
We did the examples on the problem set.
But how's that possible?
Yeah, it doesn't give you anything that you can't figure out.
You know, I do have it's usually the resources. for that.
Yeah.
Yeah, then too.
And when he was going over, it was like right before the second test. And he was like, this might be on the test, but he may have been trying. I think that's true. He doesn't, he has, he doesn't.
But it wasn't on exam 5. Problem
Yeah.
set 5.
It wasn't on problem set 5, it wasn't on your other problem set either.
I'm highly doubting it's gonna be. I hope it's not.
Be prepared for anything.
I don't have time.
Well, I can tell you out of the two, I expect this one to be on there more.
Thank
Yeah. Integrator. If you can't set this up, why would I give you an integrator?
To be fair, last year, like, it was the E shift and the I shift problems every time, but they got gradually harder. Like, first he did an E shift and then he was like, oh, you all got it wrong. Let me give you something that was way harder. And then we did even worse. And then he did one with an E shift and an I shift.
Yeah.
So I'm wondering if he'll make it an even hard, like, go to an active differentiator.
The other TA that we had.
He just,
All right, well, we'll see. It's tomorrow, so there's not too much anticipation left.
Do like a pre-plan. Pre-exam.
A pre-exam on it?
What?
A day or two to recover
Like-
from the
So wait,
exam.
it's like, quickly. You wanna go over it, do you remember, like?
I've never seen a exam problem where you do
So,
an integrator without having known Laplace so that you can turn it into a linear device, work on it that way. And then it's just that. That exact same thing. It's the same process, but you would do a Laplace transform to turn that integral of the capacitor into a linear expression where you just have an S domain term.
Would that be something that would be in the first part, like the idea of, do you do like an integral, like which would be which, or is that too complicated for the first part to do that?
The first part of the exam is more like if I'm dealing with integrals, for example, or derivative, I'm gonna ask you like, what is G sub D in terms of like, yeah, and your options, the correct answer, right, is what?
G sub D,
What do you do to get that expression.
The partial loss, the partial negative over.
Right. Which in even simpler terms means
Mass conductance.
that's more complicated. Simpler terms, what's a derivative? The slope at that point. So G sub D is the slope at your operating point. It's the linear term of it.
I always go for option D. I don't know. I don't know.
I don't recommend that. But if you're pressed for time, definitely. Don't spend a ton of time on part A. And, mess yourself up because you get to a problem like this that needs more time. Multiple choice.
Yes.
Yeah. Other questions that come up a lot are like, what's the difference of beta? Right?
For BJT and MOSFET.
Yeah, because they don't mean the same thing. They don't have the same units
Yeah.
for a reason. So you have that type of thing. That's what's on part A. So 20 questions. So 1 point a question. It's worth 20%.
20% from one.
Yeah, 20% of the final is part A. It's the multiple choice.
So
80%. It's part B.
Yeah, but don't worry. It also grades part A. You always tell them. I got. Yeah, so I mean, that's what you should expect from part A.
it doesn't go MOSFET with capacitors to
Okay, we can talk about that, because that's kind of,
the CMOS binder.
yeah.
Yeah.
Does everyone feel okay with this? With this? Like, after this point, you do your output, be careful with it, or do your symbolic solver on your Inspire. The symbolic stuff is fantastic, just be careful with it. Like for variable names, they have to start with a letter. Make sure that you do the multiplication between stuff, not just like a variable right next to another variable. That makes sense?
Yeah, I guess I have a cassia that's similar, but I don't know how to do the FXCG50.
Yes.
I like that it's got replaced. Basically, if I put that calculator in a drawer for 20 years and put new batteries in it, it'll still work.
It has spice on it.
Oh, that's great.
They're what?
Python. It fits. Graphs.
So does that Inspire.
But the
As long
Inspire,
as-
leave it in a drawer for 10 years.
The really big thing is if it has, what do they call it, computer
I think it does.
algebra, computer algebra system, or just that solver.
I think it does.
I want to learn about that.
Great. It
Can
has
I-
like,
Erase.
it has like every constant known to mankind stored in it.
But it doesn't have COX or ESI. The permittivity of silicon or relative. No, it doesn't, because I checked when I was taking my digital.
Does it do convert?
Yeah. you can-
No, there's-
No way.
Yeah.
Yeah. COX and the permittivity of silicon itself. I have one of those.
11.8 times 8.8.
For the.
Yeah, I remembered the 3.9.
3.9 is oxide.
You use it when you multiply like amps times ohms, it'll give you volts.
Here.
Yeah.
It's, yeah, I have a very good amount of calculator.
Yeah, but I always like replaceable batteries on stuff, like, an FXCG50 does have replaceable batteries.
Okay. Yeah.
Yeah, but like, no, basically, that's the fact that it's gonna last forever. The battery, they're gonna make the batteries obsolete in a few years. Yeah, gonna make batteries, no longer sell the batteries for theirs. Their proprietary rechargeable batteries.
Yep.
This is no burning out.
They're like phone batteries, smartphone batteries. They wear out. You know, I don't know what's that.
It's like. This month. Charges. What you saying? It's pretty.
Yeah. In here. I was like, why is it?
But if you're in the middle of a classroom and there's no outlet nearby, you can't move.
Well, it's pretty bad.
I keep sparing my body.
I'm still getting the ring.
Yeah.
Yeah, I have a taped up set of spares for the off chance. Yeah, 4 AAA batteries.
That's
Good
a
for
good-
you.
Oh, thanks.
All right.
But you tell.
Get back on track.
Is this what you're talking about where you're hoping he doesn't?
Yeah.
Yeah.
It doesn't go.
Capacitors.
We want that.
Okay.
Oh.
I heard a little bit about that you asked for materials on this, and then he said that it's too complicated.
Yeah.
I think he misunderstood you.
Designing amplifier.
Yes. I think he misunderstood you. You have to be kind of careful with how you phrase your
I'm not gonna.
request. I think what he thought you were asking for was like materials on how to bias up like the internals of an op-amp, which those are much more complicated. Because that's like multiple stages of this. But this, let's demystify this real quick and talk in simple terms of why these capacitors are there. If I'm going to amplify a signal, like a voice on a microphone, that signal can go positive and negative. It's a sine wave. So that input signal is going to be like this. I want my output to also have these negative values. But if my amplifier only goes from positive to ground, then it can't go negative. Right? So what I need to do is I need to shift the like zero of my amplifier. And I bias it up. I give it a bias so that now it sits halfway in between VDD and ground. So now without an input to my amplifier, my amplifier sits midway between VDD and ground. I do this because now when I introduce an input signal to the amplifier, it'll move relative to that new bias point. So now these negative parts of the signal show up still. I'm getting the full signal at the output, just shifted up. And the way that I can separate them is with these decoupling capacitors. The DC case, which gives me the bias, which sets me at VDD over 2, is set by the circuit where I treat these capacitors as open. What that looks like is just this guy right there, which is what problem set 5 has been about, which is what likely the exam question will be about, is the analysis of the bias, not necessarily the analysis of the amplifier. If we want to analyze the amplifier, Grace had a really good question yesterday of we look at input impedance, right? To this guy in the DC case. And that's these two resistors in parallel. In the AC case, it's different. In the AC case, we're including this. All of these capacitors become shorts in the AC case.
So you're blocking DC.
You're blocking DC so that you can set your bias level. And then your AC goes on top of that and it operates at your bias. So then you can do the small signal analysis. That you can look at it, inputs and outputs, and you get your actual gain of your AC signal. The reason that you want to do it at the small signal is because you want to, like Thevenin's only works with linear devices. BJT, exponential, it's not linear. So to turn it into a linear representation, you take the small signal, you take the derivative, and now this exponential term at this point, the slope is linear, right? So at this operating point, we can approximate it to be a linear device. You do small signal analysis. Now you can do Thevenin's and all that stuff that needs linear devices.
And I don't know if y'all saw Brian in the helpful office. He added me this morning or at like 2 a.m. because we talked about this for like half an hour. And what he said is when you're doing it in DC without the small signal, it becomes an output. So, you just, and it goes into the 2 quarters of what we're gonna apparently do in circuits too. But how they explained it to me was if you're trying to do a Thevenin's and something with in DC with a nonlinear device, it's just the output and you,
Right.
Yeah.
You break it up into sections, right? So you break it up and you go. This is a section of linear devices that I can turn into a Thevenin's equivalent. This will be a section of linear devices that I can turn into, or like, you can find the biasing of this, turn it into the small signal, then it'll be a linear device that you can look at. So don't be scared of the capacitor. They exist for a reason. And that reason's relatively simple. Of you want to use the DC case to get yourself at a level where this will operate the way that you need it to. And then you can introduce AC, some signal that's changing, some signal that you want to amplify by blocking any DC changes to this, but AC signal is being let through a capacitor. You can put a capacitor here because in the DC case, these two are just in series, right? So this RE can be different than the RE in the AC case. Because if I have this capacitor here, in the AC case, this shorts out. So now RE is just this. It changes it and it helps us adjust the gain in the AC. But that's something that you guys didn't really get to in this course, or did you?
we talked about it. We went through what you just said. And talked about how that's like, one is a bypass and one is a coupling capacitor.
And then you got another,
On the low.
yeah, because you don't want a loading effect from your load onto the DC case. AC.
That's electronics too, right? For the amplifier.
It should be electronics 1. I covered it in electronics 1. But it's also electronics 2. Electronics 2 is going to be more applications of both MOSFETs and BJTs. everything that I've just said for this is true over here. What's the main difference is here you don't have a gate current. Here you have a base current. So if you're solving for these, you solve them the same way. I have to take away the capacitors for now. Just look at the DC case. So for MOSFET, it's typically easier because you have no gate current. You can tell me immediately what VG is. Right. Here.
Voltage, what's the cross
The
tab?
voltage divided by.
So let's do. So. No VG. This is operating in the saturation region. You know, ID. The equation for it at least, right?
If we don't have lambda, we assume zero, not.
Yeah. Which. Do it for lambda is 0. Do I need to have VG and VS separate in? So I can just have VGS. You can say, well, I don't know VS, so I don't know VGS. But if you're given VTH or if you're given the stuff to find VTH, you know VTH, no beta. What do we need to have for ID?
R. RS.
I do, but I mean, for
To solve.
You mean from there, you wanna go to quadratic equation?
Yes. That's where problem set 5 has been.
PG, which will be. We should know. Well, that'll be a constant, and then we'll do PS in terms of ID. Times the resistor. R4. And that's when you turn it into a quadrant.
Equal, like one ID for one.
BGS. So if you have ID, you can do the quadratic in terms of BGS, and if you have BGS, or if you have one of those, into it. They're analogies, they're analogies.
Okay.
So from there, we can solve for,
Plug that in, and solutions.
and then it's just quadratic formula, right? Quadratic formula,
It's always gonna be small.
smallest one? It's the one that also gives you the valid solution of,
Yeah.
are you in saturation or not, right? Because this is
Just
saturation.
There is art. Just a little bit easier when it's being tweezed.
What he explained yesterday, he came down to IEEE, did a little crash course. He explained that it's always gonna be the smallest one because, it's a quadratic. And you can only have it be this side of the quadratic, it can't be this side. And so, and then since it's a straight line pointing downwards, the intercept for the second one is always gonna be at a lower point. And so it's always gonna be the smallest. Oh, you're.
That's what I was thinking of. Yeah. But instead of doing the quadratic, you just put it.
If you're solving for VGS, it's always gonna be the smallest one of that.
Solving for VGS.
Quadratic, or the VGS, or you can do either.
If you're solving for VGS, right, you'll get a positive and a negative one. So it'll be the one that is actually valid.
Be a positive one.
Yeah.
Be the one that make it saturation.
If you're PMOS, it might be the negative one.
Make the one that's in saturation. Use the saturation.
Yeah, saturation.
That's supposed to be.
The table.
Hmm?
It's supposed to be.
Also, that ratio equals,
You know,
just.
R3, BDD, R1.
I see. And of course, it's going to.
So like, you're not gonna know what that is, but because this one's simplified, you don't have to do that.
Yeah, and that's typically why this question is considered easier.
Yeah.
Like he gave this to us without having covered MOSFET besides the fact that it has no gate current. Because of that. And it's just like, you'd know VG instantly. With BJT, you have the issue of there's a base current. That's where you have to do
Durations.
iteration. And then, of course, don't worry too much about the sensitivity functions.
Oh, yeah, you said skip that on the problems.
That is also something that you touch on a lot more in electronics too.
Can we go over ICQ max? I know you know, but it's the maximum.
Oh.
But is it, I'm confused about performance.
Hmm.
I see it's ICQ, right?
Okay.
Same.
So. Okay. It's exponential respect to IC. You have like an operating point. You have to set like an operating point. That's ICQ, your quiescent value, your operating point value. The maximum that you could do, though, is if this was a short. Right? If this had no voltage drop across from here to here. Then it would be short. And so the maximum collector current that could exist would be that's ICQ max.
I guess it doesn't say, like on the concept, it said like, calculate ICQ, but it doesn't give a resistor.
Right, but it tells you to do it at like half of ICQ max,
You
right?
know, it says to find the resistor at half ICQ max.
Right.
Oh,
So-
I find
ICQ max,
and take half of it.
half of it, that's your ICQ.
Oh,
And now you can solve for the resistance.
okay,
And that is RC max.
perfect, that's.
Yes.
Yeah.
Yeah. Huh? You never used it?
Times two.
Cause the way he did it is he like went ahead and just,
It's included in the equation, it's multiplied by two initially.
Oh, yeah,
So.
Okay.
If you have ICQ.
right.
ICQ max.
But if I asked you to bias it at like 3/4 of ICQ max,
You have to find
Yeah.
ICQ max.
right? I know in the materials it is like that. He just goes to half, which you go to half for the same reason.
That's,
Gives you your best swing. If I bias this at 3/4 of VDD. Then I can only amplify a quarter up versus half.
could you talk about what the resistors on the website do?
These?
Could be now, it's always. Oh, that's.
These resistors here. And the way that you end up treating them is. You could solve it like this. But it's gonna be a big pain in the ass. That could be kind of like avoided if you just. Get the Thevenin's equivalent. Here.
That's the REV.
So if we want the Thevenin's equivalent here. What do we have? We have, and I don't know if he did this for you guys. Can I erase this? The MOSFET stuff?
Yeah.
Then. I have. Right, is that the same?
Yeah.
The same, so I take this, I give my Thevenin's equivalent. Gonna be.
What's the software you can do?
This is a lot easier to work with. DBB and RBB.
Yes. So you can ask the.
Right. So if I'm doing the Thevenin's resistance, I short this out. These two are now in parallel. That's RBB. VBB is just gonna be voltage divider. Give me that. So now I have this. Now I can do.
That's all.
Find IB. And IB. That makes more sense than I.
And so then, so like, on the right side, the goal of like, in the center, like halfway, right? So like on the right side, your goal is to like find that much, so you're like, at the back of precisely from that or whatever. Is there like an equivalent goal for like, which there on the right side, like you pick one side?
Or which resistor?
Like RB1 and RB2.
So that's gonna be in terms of like. What do I want RBB to be? I want there to be some input resistance to that base. So I set RB1 and RB2 based on what I want that RBB value to be.
And as far as what you want RBB to be, it's kind of just like what you want the input impedance to be.
What do you want the input impedance to be and what you want BB to be if you're setting BB to a certain value.
So in the solutions for offset five. Is pretty. Whenever you solve for IE, you did one over F. But you never, he's never shown us.
Explain what alpha is. Alpha is another way of writing beta.
Because beta's 80. But it wasn't. I don't understand when it is.
I think that's it's not necessarily one of those. I'm so understanding that. After thoughts on that.
The
Yeah. No. I knew that. I'm not here.
Yeah. This is for problem 2.
Yeah, for.
Beta F is 200.
Oh, then I looked at the wrong one.
And alpha is beta over beta plus 1.
It's always a different variable.
And so 1 over alpha.
Then, I think I understood, but
Yeah.
with this stuff.
That's like that concept of like beta linearity. Right. And we talked about that yesterday, where beta is linear for a certain range. That's that range.
That's what he was saying here. He was saying.
So you can also think about it in like moving forward to your beta value. It's gonna be valid for
We don't know this.
I know, because I was not getting this. I said, all we gotta do is go over and that's that we can be able to test.
Because you never hear our saying. You don't actually do that. I think that's what his decision will be if we all do so bad that it do something.
Second, put those iterations against these.
There again, it's the summer.
Well, I'm doing better than last semester. I got like a 30 and a 20 on my.
So what? No, I. Guessing, what he told you is he told you VBE.
Okay, so if we don't have BBE, we do the iteration.
Yes. Because when you don't have VBE, you have to tool on your own, right?
Yeah.
You just got to tell us, is it ready for VBE here?
The reason that you do the iteration is because you assume VBE.
Okay.
And then you get your IC and it's up to estimate, and then you have to plug that back into the other equation,
Into,
which is all they even.
okay, okay, that's what I thought.
Yeah. Yeah.